Privet. My name is Bruce Momjian. I am very happy to be here with you in Tver. I am on a 19-day trip. I started from Philadelphia 15 days ago. I went to Hamburg, Germany, attended a user group meeting there. We had a conference in Brussels. I attended that. Then we had a conference in Moscow that Postgres Professional put on. I attended that. Then we went to Tumen, did an event there, visited Tobolsk, which was very interesting. And now I am here. And tomorrow I'm going to Minsk. So it is a pleasure to be here. I love coming to Russia. I usually come a couple times a year. And the community is indebted to the amazing engineering that we've been able to have here in Russia. So again, I think I'm coming to St. Petersburg. We have a big conference in July. And I also hope to come to High Load, which is in November or October, late October. Those are kind of our big Postgres events for the year in Russia. Of course, we have events all over the world, probably about 3 a month. I travel about 90 days a year, which is fun. But other days, if I'm not traveling, I'm home. So it's not too bad. I am one of the Postgres core team members. I've been involved with Postgres for 24 years now, which is scary. I have worked for Enterprise DB for 14 years, which is also scary. But I like my job. I enjoy what I do. I am able to work with the community, able to attend events like this, able to do trainings like this. I'm also involved, obviously, in project management. I do some development still, add features to Postgres. So it's an exciting time, certainly for the Postgres database. You might have heard a lot of activity about Postgres in the past couple of years. When I started in 1996, there was very little activity around Postgres, but that has accelerated, and I expect it to continue accelerating. I am going to be presenting today something that I don't get a chance to do very often, and that is a full span of information about performance. Performance is a very hard topic, and I'm going to explain that in a minute. And you really do need about 3 hours to do it. So we are going to be speaking until 2100. We will take a break at 1930, for some pizza, and then come back and continue. I will be taking questions as we go. So again, if you have a question while we're talking, I would love to answer that for you. The slides that you're going to see today are on my website. So this URL right here has my slides. There are about 30 different slide presentations on that website. So I will probably be showing you not only this presentation, but probably 2 or 3 more. So again, if you see a slide and you're like, where did I see that before? It's probably from somewhere on that website, and I'll try and highlight it as I go. There are also over 500 blog entries on that website. So if you're curious about different topics, particularly including performance, feel free to look there. So I don't know what just happened. Okay. I don't know what that was, but that's okay, because the screen here was fine. I don't. Anyway. Again, I do enjoy giving this talk. Are there any questions before we get started? I am going to try and speak slowly, and I'm going to try and use simple words. So hopefully that will help people understand. I wish I could present in Russian. I probably know about 20 words, but that's not enough to Yeah, not enough. Yvonne could do it very well, I'm sure. But unfortunately, I cannot. So any questions? Okay. Again, we'll be taking a break in about 75 minutes or so. And then we'll go till 2100. So let me just talk a little bit about performance. I give a lot of talks, probably 30 or 40 talks a year, different places. And performance is a really hard topic because normally when I give a talk, it's on a specific part of Postgres. So I'll talk about the optimizer, or I'll talk about common table expressions or window functions, or I'll talk about maybe the internals of Postgres or project management. Those are specific topics. Performance is this kind of a topic that spreads all over the place. Because what people who come to a performance talk really want to know is, how do I make my system faster? Why is my system slow? How can I improve it? And the reason it's difficult is because every system has kind of a different problem. As Tolstoy said, all healthy families are the same and all dysfunctional families are different. I believe it or not, I did not know it was Tolstoy who said that. And somebody came, I had heard it, but I didn't know who it was. And I said it in a talk, and somebody came up to me later, and he said, I've never heard Tolstoy quoted in a technical talk. And I said, is that where it's from? He said, yes, that's from Anna Karenina. He was like, okay. So anyway, yes, because there's a lot of truth to that. If your system is slow, it might be because you have a server setting wrong. Your system might be slow because your queries are written in an awkward way, or the statistics are bad, or there's a server, or there, maybe there's a hardware setting that needs to be changed. So it's not like performance is not one thing, it's what is making your system dysfunctional, right? And it could be a whole bunch of different things. That's why I can't give this talk in an hour, because there's so many aspects that you need to consider. And my goal in the next 2 hours and 45 minutes is to give you a spectrum of things that you need to look for to determine if your system is running in a healthy way. Right? Again, just back to Tolstoy. You want a healthy server. You don't want a dysfunctional server. How do you find out what is dysfunctional about your system? So what I'm going to do is I'm going to walk through performance, but I'm also going to talk about some specific topics. So as we go through these slides, I'm going to show another slide deck that just deals with hardware. You might think hardware and database, why is that important? Well, there are so many databases are so critical to the hardware and how it's set up. You may not realize that, but I'm going to explain why that is. Second thing I'm going to talk about in another presentation I'm going to show you while we go on is the optimizer. You might have heard of the optimizer. You might not be sure what it does. You might not be sure how to make sure it's healthy or not, but we have to talk about the optimizer as well. Okay? So again, like Tolstoy, we're going to find out why your server is not healthy, but the answer is different for everyone here. But once you go through the talk, at the end, you'll be able to say, okay, let me look at my hardware. Is that healthy? Do I have the right settings for my hardware? Do I have the right hardware? And all right, let's try that. Okay. I just pulled down the resolution a little bit. So you're going to look, you say, is my hardware, do I have the right hardware to make a good performing system, right? And then, okay, now that I know my hardware is good, what about my server settings? Are my server settings right? Okay. And then once I have my server settings right, okay, are my queries good? Do I have the proper indexes in place? Am I writing my queries the way that I need to so they're fast, right? So all those three aspects are really important to getting good performance. And that's why this takes so long, because there's not one answer to performance. It's always different. Any questions? Okay, let's get started. Okay, so We're going to first start really simple, and we're going to talk about caching, and I'll explain why that's important in a couple minutes. Then we're going to talk about some internals, and at that point we're going to talk about the optimizer, and then finally we'll talk a little bit about storage, and then I have some suggestions at the end, and then we'll be in good shape. Okay. So caching. Why is caching? Why do you start a talk about caching? Let me see if I can explain. I have been working obviously with Postgres for 20 some years, but I have had the blessing of working in the open source area full time for 20 of those years. So since 2000, I have worked full time in the community. Why is that? It's because databases are really complicated. If you think of an email server or a web server or something, application server, pretty clear what they do, pretty clear what the workload is. Databases, no. Databases have unique requirements that really very few other pieces of software have. The first requirement is durability. When you commit a transaction, you have got to guarantee in a relational system that if you're to lose power or something was to crash, that data is durably stored on disk. Okay. Second, the workload is often very different. So sometimes you're running little queries, and then you have data warehouse queries, and then you have little queries again, and sometimes they're all running at the same time. Okay. And the third issue is that a database locks user data inside the database. So the data is kind of trapped in there, and therefore it's critical that that system run well. If your web server dies, what do? You just restart your web server, right? If your text editor dies, you just get another text editor, right? You're not wedded to, your data isn't trapped inside the text editor. It's just, you can open it with any text editor, right? Same thing with a spreadsheet or whatever, right? But with a database, no, that data is locked inside there. And the other issue is performance. Performance is critical for databases because your organization is really running and requires really good performance. So performance, durability, and variable workloads, that makes databases critical, and therefore it makes them very hard to tune. It's probably why you're here. Because if I said, oh, let's go tune a text editor, how many people would show up? Probably not many, okay? Because either it's fast or it isn't fast. If it isn't fast, I'll get a new one, right? But databases are complex, and that's why it's a big market and it's very important, okay? So again, I talked about the fact that databases have variable workloads and variable sizes of workloads. So caching becomes very important. And as you can imagine, in a typical computer, you have probably 4 levels of caching going on. And you have to understand that because effectively to get good performance, you have to make sure that you're caching everything at the right level. The closest area is the CPU registers, if you're familiar with that. Usually it's about 32 registers in a CPU, 64-bit wide. But there's obviously a limited number of those. Then you have a cache around the CPU. That could be a megabyte. What's typical cache these days? 16 megs of cache on a CPU die. Okay. Then around that cache you have the kernel cache, which is the RAM that you use to hold intermediate results and data that you haven't changed. And then at the outside is the storage. And the storage is obviously the slowest part of the whole system. But also the storage is typically the only durable part of the system. Okay? So for a database, not only are you going to use this area because you have to store things that don't fit in memory, but you often have to use that area for durability. And that's kind of critical. And as we talked about databases, we'll start to see why that's important. Okay. CPU registers typically in bytes, CPU cache typically megabytes, RAM typically gigabytes, and drives typically terabytes. There's no surprise here. it kind of makes sense that as we get farther away from the CPU, these areas become larger, okay? This diagram is absolutely critical to understanding performance in Postgres, and I'm going to spend quite a bit of time on it, but I think it shows a whole bunch of things in one display. First off, are there any questions about what I've said so far? Okay, so this is the diagram of how Postgres does things. There are several parts. There's a caching layer, which is up here. There's an area called the write-ahead log, which I'll talk about in a minute. There's recovery, which I'll talk about here. And then there's also something called a checkpoint, which I have slides for, which I'll talk about in a minute. Okay? So if you've heard the term write-ahead log or checkpoint or crash recovery, and you weren't sure maybe what they were, we're going to explain that. All right? It all relates to Postgres's good performance. It relates to durability, and it relates to having a healthy system. Okay? So let's take a look at first the easiest part, the disk. This is where you store all your data. Okay? Very simple to understand. Okay? When the server is installed, you basically create an empty database down here, an empty database cluster. Okay? To read that data, you typically read it up into the kernel. This is a variable sized area of memory, which the Linux kernel or Windows kernel or FreeBSD kernel will manage for you. Okay? And then above that is a special area in red called the shared buffer cache. Okay? So the shared buffer cache is Postgres's private shared memory area that all of the sessions can read from and write to. Okay? So for example, if you do a select on a table, okay, we first see, is that table, each is the page I want in the shared buffer cache. If it isn't, I ask the kernel, is that page, that 8K page in the kernel? If it isn't, I ask the storage. It gets read up to the kernel, and the kernel copies it into the shared buffer cache. Similarly, if I want to write to the storage, I will write a shared buffer page to the kernel cache, and the kernel cache will then write it to storage. So those are our three levels of storage. Okay, this is the physical storage, right? This is the RAM that the kernel controls, and the red part is a shared memory area, which is shared by all of the system. Now, in terms of performance, how big should this be? In Postgres, we normally recommend that the shared buffer cache area be about 25% of your entire RAM. Now, some people think it should be bigger. The problem, if you make it too big, is that the kernel buffer cache gets too small. Okay? So you don't want to make it too big. Typically, 25% is about where you want to go. You can try making it bigger, but you want to run some performance tests to make sure you're getting a benefit from making it bigger. It doesn't make it slower, because it can happen, right? So again, you start at 25% here, and then you can go up or down depending on what your testing shows. Different workloads can do better. For example, if it's a read-only workload and it processes a lot of data, you may benefit from 50% here. Okay? But if it's a read-write workload, you're probably better off at 25%. Okay? So again, depending on what your workload is here, you may want a bigger or smaller shared buffer cache to go with that. All right? As I said, all the Postgres backends can read and write to this shared buffer area. They don't request data from the kernel directly. They basically ask here first, and if they can't find it, then they ask the kernel for the data, the operating system. The operating system returns the data up into the shared buffer cache, and then they can continue processing. Any questions so far? There must be somebody who has a question. Yes, sir.
To increase the size of the RAM for Postgres shared buffer cache, then at some point kernel needs buffer cache with the size, so it will reduce. What is the, so imagine we have 25% for the upper layer, for the middle layer, what is the usual amount of memory that the kernel takes?
So how big is this? Okay. So the question is, if this is 25%, how big is this, right? So there is a command. Do you run Linux or Windows or Linux? So there's a command on Linux called free, literally the word free, F-R-E-E. And if you type the word F-R-E-E, it will tell you exactly how big the kernel buffer cache is, okay? If you go on my website, there is a blog entry that explains how to read the free output, okay? So you don't need to take my word for it. Typically, this is going to be, could be 35% of RAM, could be 40% of RAM, depending on what else happens in the system, okay? Now, some people who come from other databases have said, you know, why am I using the shared buffer cache? Why don't I use TverIO and go directly from here to here? Because this is overhead to go through this stage. Okay, I'm seeing some people nod. I do get this question, so I wanted to cover it. Okay, so we've done some research on using TverIO to copy from here to here. And what we found is we could get about 3 to 6% faster performance by eliminating this region and copying from here directly to here. However, those were ideal numbers. Those were numbers where we knew how big the workload was, and we set the shared buffer cache to exactly the right size for that workload. What we found is if this was not sized properly, okay, performance got much worse, like 30, 40% worse. Because what happens is everything that doesn't fit in here literally has to come from the storage. And I have a blog entry about this on my website. Again, if you go to my website, the blogs, at the top of the website, you'll see category index. And if you click on category index, you can see all 550 blogs in categories. And there's a specific performance category, and I probably recommend you look there because it does talk about the free command and it does talk about this double buffering, which is what we call it. What we found is this free space will get bigger or smaller depending on what other memory is being used in the system. So if the system isn't using a lot of other memory, this could be really big, right? And therefore, even if this isn't sized improperly, it's still fine because it's just copying stuff that's already here. If memory gets tight, this gets smaller, but this is always the same size, so we have good performance, okay? What we found was that the subtle thing was that when you add a feature, it might give you a performance benefit for certain workloads, but if it makes the system more fragile, more likely to give bad performance in other workloads, you have to balance those two. And that's really what we found. And if you talk to people who use TverIO, a database it's kind of true. You have to be very sensitive that this is the right size because you don't have this elastic thing underneath you. And the Postgres architecture, we looked at the benefit, and I don't know if we're ever going to do it. Now, we do use TverIO over on the right-hand side. I'm going to get to that in a minute, okay? Because that blue area really can benefit from TverIO, which I'll talk about. But over here on the left-hand side, on the left-hand side, TverIO is not really going to benefit. It might benefit us for specific workload, but it's going to make other workloads much more fragile. And as you know, databases, their workloads change all the time. At least most of them do. And we're kind of happy with that. Yes, sir, you have a question.
What type of workload did you estimate to see the performance benefit of eliminating kernel disk buffer cache from this?
Right. So what happens is if the kernel cache, well, I have to define a term. The term we use in computer science for this is working set. So how much data does the system look at in a 5-minute period, let's say, okay? And we'll call that working set. Maybe it's 100 megabytes. So if your working set for your database is 100 megabytes, meaning it looks at 100 megabytes per every 5 minutes, if this is 100 megabytes, you're good with DirectIO because it's all going to fit in there. You're not going to have to hit the disk very much. You're good. If your workload changes to 200 megabytes all of a sudden, okay?
I mean, the type of workload, was it like read-only, write-only, or was it like?
Okay, so there are two types of So the two types of workloads that make it fragile is if you're doing a read-only workload and the data doesn't fit in the shared buffer cache. Cache is smaller, and we don't have this elastic backup. Okay. The other workload where it doesn't work well are read-write workloads. If you write too many into here and we can't flush them down here quick enough, we don't have an area here to absorb the writes. Right now, we can absorb the writes real fast. We just throw them to the kernel. We can throw away that buffer. Done. Okay, let's keep moving. All right. You don't have to wait for the data to get down to the storage, particularly because of the write-ahead log. I'll explain that in a minute. But you're not having to wait. So you're just throwing stuff down there, and you don't care kind of when it gets to the disk. So the one workload where it helps is, again, a read-only workload where your shared buffer cache is the right size. But again, if your right size for your shared buffer cache is 65% of RAM, then you're only leaving 35% for everyone else. And that might be too tight. So then you say, oh, well, maybe I need to make it 50%. But then if I make it 50% and my workload is really 65%, then you're going to get bad performance. You see what I mean? This kind of elastic area really covers over a lot of problems or inconsistencies. And most people who have a web server, an email server, they know what their volume is. It's the same volume every day. Like, there's no real spikes. But databases always have spikes. People are running data warehouse queries, huge orders come in, right? It's a very spiky workload. Databases always have. So getting that red area to be the right size is kind of weird. Again, if you're running other databases, they have tools, and you sit and you look at the reports, and then you play with it. But in Postgres, we don't assume somebody's doing that. We don't assume there's a DBA sometimes. So we're just kind of like, this is a good general solution. It's not ideal. We're losing 3 to 6%. But what we find is that when Postgres does things, it can handle workloads that are very variable better because of that architecture. Thank you. Other questions? And those were great questions. That's exactly what we wanted to cover in that. So having talked about how this stage works, I want to come over here. Okay. So do you remember I talked about durability? What is durability? Durability says that when you commit a transaction, that transaction is stored on some durable media. It doesn't define what it is. Typically, it's an SSD, battery-backed RAM. It could be magnetic storage, a magnetic disk. Okay, but some durable media. So if power disappears, the data is stored. It doesn't prevent from every disaster. If a comet comes and hits the server, it's not durable. I'm sorry. It's going to be a molten thing of lead, right? We can't fix everything. But durability typically means that loss of power, kernel failure, kernel panic, whatever, your data is going to be reliable, okay, stored. So how does Postgres do that, or how does general systems do it? What they typically do is they have a process where they write a continuous stream of changes to a fixed location. So I might have a transaction or a query that changes 5 different tables, okay? But what I want to do, if I'm going to make it durable, is I want to write those changes into a log. In this case, it's called the write-ahead log. And it's basically just a list of changes. I inserted this row, I deleted that row, I created this table, I dropped that index. Whatever I did in the database, I'm going to create a stream of changes, okay? And what I'm going to do is I'm going to write those into memory. And before I commit my transaction, before I say my transaction is durable, I am going to guarantee that those changes have been written to some durable location. All right? What that means is you have a write-ahead log, you write it to the kernel optionally, and then the kernel writes it to some kind of permanent storage. Again, this could be battery-backed RAM, this could be an SSD, this could be magnetic disk, something. And I have another talk we're going to talk about in a minute, which actually goes into the hardware layers, because as I said at the beginning, one of the 3 aspects of performance is hardware. Okay? So I'm going to write the write-ahead log. Now, if I turn on a Postgres setting, I can use DirectIO here. Okay? Because all I really want to do is I want to get it from here to here. I don't care about the kernel. I don't care about it staying there. I need it written right away. I'm never going to read it back again, probably. So again, there is a setting in Postgres, and it's called fsync method. It's called fsync method, and it effectively controls whether DirectIO is done here. There's a couple different. There's fdatasync. There's fosync. There's a whole bunch of different settings. But you look at fsync method, you'll see the various options that are chosen. And there are different defaults. For example, in Linux, there's one default. On Windows, there's a different default. I don't remember if FreeBSD has the same default as Linux or a different one. I think they seem to have a different default. But again, those default methods of how to write this as fast as possible, not to the kernel, because this is not durable, but down here, okay? And I'll talk to you a little later about SSDs and RAID controllers and stuff like that. There are some optimizations we can make here which make tremendous difference in performance. Tremendous, like between 60 commits a second and 6,000 commits a second. Okay, 100x changes in commit performance by having the right settings here, but also having the right hardware here. And I have a separate presentation we're going to go into in a minute, which actually goes into all of those settings. Again, maybe it wasn't obvious. It's not obvious sometimes, but sometimes small amounts of hardware, a couple $100. Hey, if somebody can make my server 100 times faster for $300, where do I buy it, right? But you have to know that you need it. You have to know that you need it. Okay, and I have a great talk we're going to have in a minute, which talks about that. The bottom line is when you think of hardware, databases are different. And we're going to talk about that. Okay. Any questions about this so far? Yes, sir. Yeah, I'll repeat the question, or would you like it in Russian? I'm sorry. Great. Thank you.
Okay, my question is, what could be the reason to pass the updates from write-ahead log to the disk through the kernel disk buffer cache?
Okay.
What are the benefits?
There are no
because
benefits.
We are still waiting for fsync.
Right. So the traditional way that you would do this is you would write the write-ahead log to the kernel buffer cache, and then you would issue a separate function kernel call called fdatasync. And what fdatasync would say is take everything that's associated with that particular file and flush it to disk. So it's write, sends it from here to here, fdatasync sends it from here to here. There is a special kernel call called, it's fosync, which will effectively automatically sync things directly. There's an odirect option in in Postgres, which will basically issue the write with the ODirect flag. When it opens the file, the write-ahead log file, it opens it with the ODirect flag. And therefore, any write to that write-ahead log file bypasses the kernel right away and just goes right to the disk.
And why is it not the default?
It is the default for some operating systems, but not every operating system has direct I/O. So we have to kind of, we support a lot of different operating systems. So some of them don't have it, or it doesn't work, or it's slow. For example, in Linux, I think OData Sync is the fastest, but then on FreeBSD, I think it's still FData Sync and not O. Anyway, the bottom line is we've had different platforms test the options, okay?
Got it.
And we get the best numbers. The good news is that there is a utility that is shipped with Postgres, which will test all the sync methods for you. Mm-hmm. So it's just called PGF sync. I wrote it, so I think it works. It's in the bin directory, and you just type PG_F sync, and it tests all the sync methods for your operating system. It gives you times of how long each sync method took. And you basically just look which one is the fastest, and you go into if that's not the default for your operating system, you go and you change it. Because different versions of Linux have different optimizations they're not hugely different, but why not use the fastest one?
Yeah, for sure.
Yeah.
Thank you.
But PGF data sync, I think it's just PGF sync, is really the tool you should be using, because it just runs all those tests for you, and you don't have to worry about it. It does 8K blocks and then runs it thousands of times. You're also going to see different numbers on, like, if you run it on an SSD, you'll see faster numbers in magnetic and so forth. So it's kind of nice.
Okay. Thank you so much.
Great. Other questions? I should have mentioned that tool. Thank you.
To optimize maybe to reduce some layers and make a Postgres like an operating system on its own file system and so on and so forth.
Yeah. So we have discussed that frequently. And we've really rejected that idea, and let me explain why. So when Oracle and DB2 originally were being developed, Unix operating systems did not have very good file systems. So I'm not sure if you remember, System 5 Release 3 had a file system, that was pretty fragmented, didn't get good throughput. There was one on HPUX, which was kind of like, it worked, but it didn't have really good performance. So a lot of the databases in the 80s and 90s, to get good performance out of Unix, had to write their own file systems. And they had to rewrite a whole bunch of different parts of the operating system that were slow. But if you look at it today, most of the operating systems have really good I/O. In fact, they have choices. Like, people think, for example, ext2 was fairly poor in performance. ext4 is actually really good. A lot of people like XFS. ZFS, I've heard, not great things about. I know it has a lot of features, ZFS, but in terms of performance, XFS or ext2 are faster, okay? So my point is, we're probably not going to be able to write a much better file system than what these people are already doing. The other issue that I think shows some wisdom is that Postgres, as the cloud has become more popular, Postgres never re-implemented the operating system. So it runs on almost any cloud with no changes. Perfectly great performance, okay? All of the databases which have replaced parts of the operating system, their performance on cloud becomes much more difficult because they're having to talk to the hardware at a much lower level. At the Postgres level, we've always just kind of said, There's an operating system down there. We're going to let them do their job, and we're not going to interfere. So if we're running in a container, if we're running on a virtual machine, we don't care. And that has actually made Postgres really, really popular in cloud deployments that make things like Oracle and DB2 very difficult. So we didn't do it for that reason. We did it for other reasons. But in fact, looking back, it's actually was a very good choice because we have been able to benefit from XFS and ext4, but also we've been able to move into the cloud very smoothly, much smoother than most databases. Okay, other questions? Okay, great. Okay, and again, this may be the most complicated slide for what we're going to talk about before the pizza. After the pizza, going to be more. Before the pizza, this is your complicated before the pizza slide. Let's talk up here about recovery. Okay, so I've talked about two things so far. I've talked about how Postgres reads and writes its data. I've talked about how it does durability. What about crash recovery? When Postgres starts, how does it do crash recovery? When it starts, it basically looks at the write-ahead log and it says, did Postgres shut down cleanly or not? Is there a record at the end of the write-ahead log that says I'm shutting down? And if there's no record like that, it means it crashed. So what it does is on recovery, if there's not a nice record at the end that says I'm good, it's going to replay all the changes from the last checkpoint. I haven't talked about checkpoints yet, but I will. I'm going to replay everything from the last checkpoint. I'm going to read it up into a special Postgres server. I'm going to replay it into the shared buffers, and I'm going to write it down to the kernel. And once I'm done that process, I can now start up because now I've got durability again. Okay? So that's how durability works, is effectively you're writing all these change records. When you start up, was it a clean shutdown? If it was not, then I'm going to read the write-ahead log back to a certain point, and I'm going to replay all the changes to make sure everything is consistent. Not only is this write-ahead log used for crash recovery, it's used for point-in-time recovery if you want to recover to a certain point in time. It's used for replication, okay, between two servers, and it's used for logical replication. So again, incredibly useful piece of data here, used for crash recovery, used for point-in-time recovery, continuous archiving, if you've ever done that, and also used for streaming and logical replication. So really, really useful stuff. Any questions about recovery? Okay, so the last thing I want to talk about is checkpoints. Now, I have to admit, when I was a developer in the 90s, I heard the word checkpoint a lot. I wasn't sure exactly what it was. It had something to do with durability. So here's the issue. Write-ahead log. We're writing to it. Well, how long can we keep writing to it? Would we write to it do we have 5 days of write-ahead logs, 5 weeks of write-ahead logs? When does it end, right? That's a lot of data, right? You probably change a lot of data in 5 minutes, let alone 5 days, right? So the question is, how can we run a system that's recording changes and keep not too much data, right? And the way we do that is something called a checkpoint. So at a certain point in time, typically every 5 minutes, although it can change, what happens is a special process runs in the background called a checkpointer. And what it does is it goes to the shared buffer cache and it finds every dirty page. I've marked these with ones here. See the ones? And it remembers the point in the write-ahead log where it started. That's the first line. And while this is happening, people are dirtying more pages, right? Like all the twos, they're dirtying those pages. So I've got ones up there which are dirty, and while I'm doing this, looking, I'm getting more dirty pages. But that's okay. Because what I'm going to do during my checkpoint is I'm going to take all the ones and I'm going to write those to durable storage. I'm going to write them here, and then I'm going to f-sync them down here. Okay? And once I'm done that, this is my last point. This is where my write-ahead log ends. And what I'm going to do is I'm going to take this block, which is before my checkpoint started. Remember, my checkpoint started right here. This was before. And I'm going to take that block and I'm going to move it back and be the next block. And I'm going to throw away everything before that arrow. I'm just going to either recycle or I'm just going to return to the operating system. And this happens every 5 minutes. So what that means is even though I'm f-syncing like this, I don't have any more than 5 or 10 minutes of write-ahead log on disk. Right? So that's what a checkpoint does. It effectively allows me to keep a reasonable amount of write-ahead log data, but also to trim it by writing all of the dirty buffers down to durable storage at certain intervals. Any questions?
I think that the main question is to just explain everybody what dirty pages are.
Okay, so what is a dirty page? The question is, what is a dirty page? A dirty page is merely a page in the shared buffer cache which has been modified. So it might be a new page. It might be a page that we read in from disk and we changed somehow. So any page that's either new or has been changed from what's on disk has to be written down during a checkpoint. Okay? We're good? Okay. Let me just give you a little feeling for what the memory looks like on a server. Okay? Because you kind of have to have a visual of it. Down here at the bottom, we have our kernel. We know that's an elastic size, remember, depending on how much other things are going on. We have a free amount, which is not being used, probably for cache. Then we have the kernel buffer cache. Then we have our shared buffer cache. This is fixed. And then we also have a field called workmem. Workmem in Postgres is for process local memory. So any sorting or hashing that you're doing in your session, you're not doing it in the shared buffer cache, you're doing it in local memory. So there is a setting called workmem in Postgres, and it's another thing that you can use your data for. If your system becomes memory constrained, you will typically start writing things out to the swap area. I know some people don't use swap anymore, but I do recommend you have some swap on your system. If you want to look at the blog entry I have about swap, you can see why swap is important. But I will tell you, writing out the swap is not a problem, but anytime you have to read from swap, your system performance is going to be really bad. So just keep an eye on that. Different operating systems measure it differently. I do have a blog entry that talks about where to see that number. But again, anytime you're reading data from swap, it means your processes are stopping while you're waiting for data to come in because of memory constraints. So again, that might be a good reason to look at that free amount, particularly in Linux, and make sure it doesn't get too low. Questions? Okay. So let's look at the key values that you're typically going to be changing in Postgres. The one is the shared buffer command. That is, again, typically very small, just embarrassingly small. So don't use that. Just make it 25% of your RAM. This is used for temporary tables, depending on how much temporary tables you're using. This is the workmem. This is used for shared buffers, for sorts and hashes. Again, you probably want to increase that, but be careful. Same thing with maintenance workmem. This one's an interesting one. This number is the free number from Linux. So this number is effectively how big is your kernel cache. And the reason that's important is it tells the optimizer how much memory is probably sitting underneath me in the kernel. It doesn't allocate any size. It's merely telling the optimizer how big of a kernel cache do you think I have. And again, that can be important to encourage index scans if you do have a lot of free memory in your kernel by changing that value. And again, these are the 5 values that I think are pretty important and you can understand why, having talked about write-ahead log. And again, another one, fsync method, which I don't have on here, but running pgtest fsync. It's called pgtest fsync. That's what it's called. pgtest fsync. I wrote it. I can't even remember the name. It's so long ago. But anyway, pgtest fsync will tell you what to set for fsync method if the default is not the fastest for yours. Okay. So I want to move to another presentation. Why have we changed slides? because I've explained to you the importance of fsync and the write-ahead log and checkpoints and so forth. You're now ready to understand this presentation. And again, I said there's 3 different aspects of performance. There's hardware, there's tuning parameters, and then there's the optimizer. Okay? So we're going to talk about hardware. We're probably going to have some pizza after that. Just let you know. Probably going to have some pizza after this, and then we come back. We're probably going to talk about the optimizer, and then probably talk about some other issues like storage and so forth. Okay? But I want to back up, and I want to just talk about hardware because we already talked about how the fsync works and why it's important. We're going to talk here. Any questions before I start? And again, this is the same website. Everything's there. Yes, sir.
I'm sorry. I wanted to ask about the previous slide about
Yes.
the swap. If the server has no swap, what's going to be with Postgres process?
Okay. So the question is, what do you do if you have no swap? So if you have I guess I'll talk about the blog entry. So when you're running a process in RAM, typical process is going to be, 500 kilobytes or maybe a meg or a megabyte and a half. And typically an executable has maybe 100 or 150 kilobytes at the beginning, which is just used to initialize the application. You're never going to run that again. You initialized it, you're done. So if you get low on memory and you have a swap area, the operating system will say, this process is a megabyte and a half, but there's 300 kilobytes at the beginning that this process hasn't touched in hours, right? So it's going to take that and potentially copy it. It might be some data area. It's not the code itself. It's the data that was allocated for initialization, which you probably haven't touched in a long time. And it's going to copy that to swap in case you need it later. If you don't have a swap area, the kernel is going to not do that. It can't start to move stuff out to swap, hoping you're never going to need it. And that's why I tell people, you don't have to make the swap big, but it should be a couple gigabytes just to give the operating system, if things get tight, give the operating system a way out, a way of sort of freeing up some stuff really fast. And the reason people feel they don't need it is I have so much RAM, I don't need to worry about it. But with a database, you don't know exactly how much memory. Maybe you made work mem too high. Maybe there's a lot of sorts going on and the kernel's getting worried. If you define a swap area, there's a way of giving you an exit, okay? And also, if you start seeing the swap being used, you might think, maybe I'm low on memory, right? So it's kind of a warning sign as well. So that's why I recommend, even though it's not expensive, I say just use the swap area, allow old stuff to go out there. But again, if you need to read stuff in from swap, then something's very wrong. Because again, if you take initialization data and you put it out to swap, you're never going to need it again. That's okay. But if you actually do need it, then your system is going to be unbelievably slow. because it's going to say, oh, I want to call that function. Oh, okay, let me go bring this back from disk. Okay, here it is. You know, the system will be just terrible. So again, I think that swapping things out is fine. Swapping things back is a disaster. But I do recommend it. And most people agree that probably it does make sense.
I just ask it because typical setting swap is like half of RAM. It's too much, right?
It's probably half of RAM is way too much. Yeah, I would say a couple gigabytes is probably going to be fine. You're not going to have that much data that you don't touch, right? But I see it as a relief valve for the operating system and something to alert you if you start seeing things happening in the swap. Then you need something's wrong, something's tight. If you don't have swap, you're not going to know that because it can't. Yeah, makes sense. Yeah. Other questions? That's a good question. Okay, so let's talk about hardware. Again, I said this is really important. So when people think of buying a computer, these are the things they think about. Okay, you know, how many CPUs, how fast is it, what is it, right? But the bottom line is for databases, they really don't matter very much, okay? This is how they think of their computer. But they really should be thinking of it that way because most database servers are not CPU bound. They're IO bound. So when you think of speccing out a database server, don't start worrying about the CPU, start worrying about the IO first. Okay? And this is something that I think is very helpful because what typically happens in organizations is when they're deciding hardware for a web server, they use the same criteria for a database server. Doesn't make any sense. A web server has a completely different workload than a database server. So why would you choose the same type of hardware between the two, right? The I/O is critical for, and I'm going to explain why. I/O is critical for your server. Then memory, and then finally CPU. Most systems, if you look at them, they're mostly CPU idle. They're just not busy at the CPU level. They're busy down here. They may be constrained here. Typically, CPU is not a problem. That's not true of everyone. I'll talk about that in a minute. But in general, this is the mental model you should think of when you're looking at database hardware. Okay? So, why? Traditional servers often are CPU constrained because network overhead, text processing, virtual machines, application code, all CPU-based operations. Databases, large sequential scans. Do web servers do large sequential scans? I don't think so. Index scans and random I/O. I can't think of an application that does random I/O except the database. I'm sure there are some, but pretty much databases do a lot of random I/O, okay? And that can be really slow. Unpredictable query requirements. Somebody launches a 1-hour query, right? And reporting. Again, these are not major CPU issues. Hey, look at this. We know everything on this slide. We know this part on the left. We know durability on the right. We know the recovery. And we know the checkpoint. Why is that helpful? Well, let's break it down, okay? We know the shared buffer cache. We know the kernel buffer cache. But you remember I talked about the write-ahead log, this part right here. And I said I was going to get more detailed on it. Well, here it is, okay? Typically, in a magnetic disk server, you're going to issue the write-ahead log. It's going to write to the kernel cache. It's going to then write the kernel cache to an HBA, host bus adapter, which typically controls your storage. Then it's going to write it to the disk cache on the magnetic disk, which then is going to write it to the magnetic disk. And this write cache had better be write through and not write back. I'm not sure how many of you are aware, but if you run a server, a database server, where your disk cache is not battery backed and it's marked as write back, meaning it writes back right away before it gets to storage, you will get corruption on power failure. Okay? A lot of database administrators may not know this because they started with application servers, then moved to databases. Okay? But there's a specific parameter, and I'm sorry I can't show it to you because I don't have internet. There's a specific HD parm parameter in Linux, and there's a special setting on Windows which allows you to look for a specific drive. Is my cache write through or is my cache write back? If this is not durable data, if this is not going to survive a power failure, it better be write through. Okay? Now, if you have a battery in your host bus adapter or your disk controller, then you can write it back right here without even waiting for it to get down here. Isn't that cool? Okay? And typically the host bus adapter will turn off the write back cache and make sure this is right through. It actually has some smarts about that in the ATA command set that makes sure that this is durable. You've got a battery here, power goes away, this actually retains the data. So I was talking about getting 100 times commit performance improvement. You go from here to here 100 times. Okay? Because all of a sudden you can immediately write to the memory on the HBA and not have to wait. Okay? What about solid state disk? That's interesting. Well, you may have a battery here. You may have a battery here. This is a concern. If you are using a solid state disk with NAND, okay, with standard SSD, there is always a staging area. If that staging area does not have a battery or a capacitor on it, you will lose data on a power failure. When SSDs came out, everyone thought, oh, these are going to be great for databases. A whole bunch of people started using them, but they were using SSDs that did not have a battery, did not have a capacitor, and they were losing data and corrupting their databases. So anytime you get a solid state disk, you have got to make sure if it doesn't say there's a supercapacitor on there or a battery, typically it's a supercapacitor, then don't buy it for an enterprise. If you want to put media on it or you want to run games on it, go ahead. But don't probably use Postgres because you can't even turn off the cache here. You can't even get a write-through cache. You'd burn out the SSD right away. Okay, so this is more than a cache. Right here it said it's a disk cache. This is a staging area. This is not optional. You can't turn that off because of the way NAND is written. I think it's 128 kilobytes a segment, and if you turn off the cache and you make it right through, it'll burn out your SSD pretty quickly. I don't know how people know this, but it's pretty important. So you should always have an SSD with some type of supercapacitor. Another kind of SSD we're seeing is the DRAM ones. Those always come with batteries because DRAM isn't even durable. So if there was no battery, everything would disappear as soon as you hooked the power up, right? Which nobody wants, right? Any questions about that? Is that a surprise to any? Well, I'm not going to ask.
How widespread is the problem for the SSDs without a staging cache capacitor or battery? I mean, how probable is the chance that you face with a problem using just a cheap SSD?
Cheap SSD does not have it. Any consumer grade SSD typically doesn't have a battery because it doesn't need durability. It's like, oh, I saved my spreadsheet. Oh, I lost power. Oh, I'll retype it. Like, that's the way people think. Consumers, it's expensive to have a supercapacitor on your SSD. So if it's an enterprise SSD, it will have it. But most consumer drives don't have it because they don't care about durability. They don't care about losing documents in a power failure.
I mean that even for production usage and not for laptops, a lot of databases are baked with cheap SSD, even some cloud or in some dedicated hostings. And how probable is the chance that you can face with any loose data problem using data SSD?
Right. So the criteria that we recommend for Postgres is that you look at the drive, you look at the model number, and you pull up the sheet that describes the drive. And if it has a supercapacitor, it will clearly state that. If it does not clearly state that it has a supercapacitor, you have to assume it does not. So that's a problem. Now, you could decide that when I lose power, I'm going to fail over to another system. That's the way they do it in cloud. So when they lose power, they just fail over and potentially lose transactions, right? I don't want to do that on my server. I don't want to lose transactions because I tried to save $50 to have an SSD without a battery, right? Because again, this is exactly what I said before. The average server doesn't care. So you typically get, even in consumer and some enterprise that don't care about durability, they're not caring about this. So because they're thinking this way, right?
That was the reason I was asking. Actually.
Yeah. You really have to read the spec sheet, and if it does not say there is a supercapacitor, then you have to assume that staging area is not durable, and that staging area cannot be shut off. It can't be turned off, and therefore that drive should not be used for database. Yes, sir.
So you say that there is in a spec we will see that it has supercapacitor, but at what level? At the second level or on the third
No,
level?
I'm sorry. The SSD will have the supercapacitor.
All right.
Yeah, this is one device here.
And
yeah.
above that? The level
Above this, now actually this is a good point. So some HBA controllers have batteries and some of them don't. So again, you will see from the spec sheet whether it has a battery or not.
And it will specify at what level the battery is?
The kernel, yes. So when the battery is here, it will acknowledge the writes immediately because it knows they're durable. It won't wait for it to get down to here.
Yeah, what I'm saying is because we should be looking for this solution that you have on the screen.
You can. I mean, if you buy this, you can put cheap disks down here. But no, you can't, because if you put cheap SSDs down here, you still have the same problem. So yeah, I wouldn't. You used to see a lot of this when SSDs didn't exist with batteries. Now that we have SSD with batteries, most people are not getting rid of this. They're not. I have a blog entry about that. When you have SSDs, do you really need this anymore? And some people will say no. In fact, this is another place to fail. And maybe you're just better off going from the kernel right to the SSD and not using this has become much less popular. This whole layer here is much less popular because when you had magnetic disks, you kind of needed this. But now that you have the SSDs with the thing, it's like, I don't really need this anymore. I do have a blog entry about it, and there was an interesting email exchange about 18 months ago, which started to say, I don't think I need this anymore. My server doesn't have that. It doesn't need it because I have the battery now at a better place. Just some terms defining write back, returns right away, write through, waits for acknowledgement. We talked about that. Caching layers, HBA, storage of the drive. Again, enterprise and SaaS stores usually have write through. Consumers typically write back. HBA stuff, non-volatile cache, magnetic disk selection. If you're still buying magnetic disks, RAID 10 is typically what we recommend for databases. We do not recommend RAID 5 or RAID 6. That is because writes to RAID 5 and RAID 6 are slow. So again, unless you're doing read-only queries, you're probably better off with RAID 10. Another thing, any database server should be running with smart turned on, smart reporting. How many people know what smart reporting is? Okay, all right, I'll tell you. Okay, so smart reporting is a tool in your operating system which periodically checks the health of your storage. And if it sees something unusual, it will send you an email. Okay? I have been running smart reporting for, I guess, a decade or more. Last week, I got an email that said that one of my magnetic drives had a read error. So I called my wife on the phone and I said, we're going to reboot the server. I have a backup drive already in the cabinet and it's already a copy of the data. So I said, you're going to need to go get a different drive that I have in the safe and put it in the cabinet. And then we're going to reconfigure the drives because I have a drive that's failing, right? So I was able to fix it in 20 minutes. No loss of data. Everything was good. I had a full copy of the data from the night before on a backup drive that I already had. But if I didn't have smart reporting on, could have gone days, weeks, where data was just kind of disappearing. I might not have seen it. I might not have seen it in the kernel logs. Smart reporting is like the warning, you know, when you're driving and your like dash light goes on that you have like there's something wrong with the engine. That's what smart reporting is. You want that warning. You want the warning early. As soon as the system is the storage is starting to report errors, you want to hear about them right away. So I tell everybody who's running a database, turn on smart reporting for all of your storage devices and just leave it sit there. It's not going to bother you. As long as nothing wrong is happening, it's completely silent. But when you get that email one day, you'll be glad you turned it on. All right. SAS and SCSI disks. Disks are not all the same. I know they sort of say they are, but mean time between failure is somewhat different between different drives. Typically, enterprise drives are designed for this kind of workload. I was talking to somebody who works in New York, and he's responsible for a medical lab that has disks. And we were talking about replacing bad drives. And I said, I haven't replaced a bad drive. Well, at that point, I didn't have my failure that I just had last week. But he said I'm replacing them like every 18 months a different drive. And I said, wow, that seems like a lot. I've run like 10, 15 years with the same drive, without failures. I changed the drives, but he said, what kind of drives do you buy? I'm like, well, I buy, not high end, but I don't buy the cheapest drives. He said, oh, well, our company, we have to buy the cheapest drives. So to save $30, he's replacing drives every 18 months. I'm like, okay, whatever. I often find there's a middle point for drives that, you don't have to buy the best one, but typically the cheapest ones are, I don't like changing drives. I'd rather just literally keep going and not have to worry about it. SSDs. SSDs versus DRAM. Again, both are pretty fast. There is a staging area. It's not just a cache. You can't turn off the cache, typically. SSDs are not that much faster than magnetic disk for sequential I/O. But for random I/O, they're like unbelievably fast. Okay, so again, sequential I/O, it's not that big a deal. But for random I/O, it's huge. So indexes, great to put on SSDs. Huge difference. Also, the write-ahead log, because that RAM, that staging area is durable, you can f-sync to that drive really quickly, right? Because you're not having to wait for it to get onto platters. You just write it to the cache of the drive. The cache of the drive is already durable, right? So it can acknowledge it right away. You see where I'm getting at here? I'll back up. Right here. I can acknowledge right as soon as I get here. I don't have to wait for it to get here, right? Really fast. Compared to this is like I got to wait to get down here. This is like really slow, okay? So again, huge difference. If you are using SSDs, consider changing random page cost. And if you use a mixture of SSDs and magnetic, you can set random page cost per table space. So if you have some table spaces that use SSDs, set the random page cost on those table spaces to 1.1, leave them at the default of 4 on the other table spaces. Kind of cool, okay? Effective I/O concurrency, turn that on for SSDs. SSDs can take hundreds of concurrent requests. Can't do that with magnetic disk. But SSDs can consume a huge number of requests simultaneously and return them without problem. It's impossible on a disk because you got to physically move the thing around. Okay, I happen to use the Intel SSD 320. Again, this is an old drive. I wouldn't recommend it, but again, that's the class of drive you should be looking for in an enterprise, not a consumer one, typically. Okay. File system options, as I said before, XFS and ext4 are preferred. ext3 not so much. ZFS. You can reduce system logging a little bit for the wall directory, but again, not that big a deal. Battery-backed unit. This is effectively what you would see on either an HBA or on an SSD. You should be able to see the supercapacitor typically on the bottom of an SSD, right? It'll be blue or whatever. So again, make sure this is more talking about the battery that's used in an HBA. This is actually an HBA, and here's the battery right here, kind of blown up. This is the battery of an HBA. It literally are batteries. Okay, this is a supercapacitor backed unit, and I believe the supercapacitors are here, right here. These are the supercapacitors. This is the RAM. Okay, and I don't know what these. Oh, this is the microcontroller. Okay, but this is literally what makes that SSD battery backed and makes it suitable for a enterprise. And again, a database. There's a picture from Wikipedia if you're curious. Okay, shared storage. If you're using shared storage, we're almost at pizza time, by the way. If you're using shared storage, just be aware that it is shared storage. So you're not going to get the same performance characteristics out of it. It's easier to use, it's easier to manage, but it's shared. Okay? So the bottom line is databases will often wait for I/O completion, meaning they have to contend with shared resources. I'm not saying don't do it, but I am saying that you're not going to get as good performance when using a shared storage as you are direct attached storage. So just be aware of that. I'm sure a lot of you are running databases on network attached storage. Nothing wrong with that, but be aware that if performance is critical, you might want to consider at least testing direct attached storage where there's no contention for that resource. Okay, RAM. The second aspect, more is better. Put a lot of money there. Don't put the money necessarily in CPUs. More is better. 5 minutes of your working set is good. Also, make sure you get ECC RAM on your database. There's nothing worse than having your database corrupt because your RAM corrupted it. They've even done experiments where they take a server and they put it on a mountain, and then they put one at sea level and they compare the error rates, and the one on the mountain has more error rates. It's nothing wrong with the RAM. It's cosmic rays. Just because you're higher, you have less air to to block the cosmic rays. So it's literally an issue. So I would not go cheap here. I would always get a server that had ECC RAM for a database, production database. Okay, CPUs. Again, the last thing. Parallel query, you can use multiple CPUs on. If you do a lot of server-side functions like GIS, you might need more CPU there. Okay, so if you're doing server-side functions, maybe you need a big CPU. And also CPUs can be a bottleneck if the entire database fits in RAM and the workload is read-only. So you're not using I/O at all, right? Everything's in RAM. We're not writing anything. Then we might care about the CPUs. So what I'm trying to explain is normally you don't care about the CPUs, but here's where you would care about them. Okay. So bottom line, these are all cars, but they're not all the same car. They don't have the same performance characteristics. The same thing is true of hardware. You can have a different storages, different caching, different RAM amounts, and they do perform differently. Okay, so just because something has the same interface doesn't mean it has the same capabilities. And that's what I wanted to finish with. And I believe it is pizza time. And we're going to take a 20-minute break. And we come back. We're going to talk about the optimizer. So let's take a look at internals of Postgres to understand how it works. Effectively, you have a query like this, and it basically returns that row. And we're looking at how long it takes to do this part from the time you request to the time you get the answer. And the way that works, it goes into a library, typically something called libpq. It sends it over the network, and then the answer comes back. This is what the packet looks like. This is what the internals look like. That's what the thing, very confusing. But what we're going to look at is the optimizer. So when the query arrives, it gets parsed. And then, if it's a utility command, it goes over to here. But if it's a select, insert, update, or delete, it goes to the rewriter. And then here is where the interesting part happens. It's effectively the optimizer where the system decides what is the fastest way to execute that query. And then we get an execution plan. And you can actually see here the parser and how long it takes, parse analysis, how long that takes, the rewriter, how long that takes, the planner, which is also the optimizer, how long that takes, and then finally the executor. So what I'm doing is I'm taking these stages and I'm showing you how long they take. Okay? So I'm going to hop out of this presentation again. The optimizer is the brain of the database. It's very useful. It allows you to issue simple queries, and the system decides how to bring the result back as quickly as possible. How does it do that? It's got to choose something called a scan method. It's got to choose something called a join method, and it has to choose something called a join order, and I'm going to explain what those are. However, for example, this is the various scan methods: sequential scan, bitmap scan, and index scan. But let's actually set things up first. So what I'm going to do is I'm going to look at the system tables, and I'm going to look at all of the relation names. And I'm going to cut off the first letter, and I'm going to create a temporary table that has the first letter and then a whole bunch of X's. And I'm going to put an index on it. Now, if you're curious about this presentation, you can actually download the SQL of this presentation and run it in your computer. So you download the SQL file, you pipe it into PSQL, and the whole presentation will just fly by on your screen. Okay? I'm also going to create a function, and let's look at the distribution. So in this case, in this table sample, we have 78% are P's. Okay? 3.6% are S, 3.2% are C, and all the way down to I and K, which are 0.4%. 0.4%. Okay. So let's look at the optimizer. It should give us different results depending on how common the constant is. That's what optimizers are supposed to do. So when I issue a P, I get an index scan. When I issue a D, I get an index scan. And when I issue a K, which is the rarest value, I also get an index scan. That seems weird because it's not really doing anything smart, is it? However, that's because we don't have any statistics. Statistics are automatically generated for Postgres based on anytime insert or delete activity or update activity happens in a table. But it isn't executed on temporary tables, and this happens to be a temporary table, so I have to issue the analyze command itself to get statistics. And as soon as I issue the analyze command, you notice that the P, which used to be an index scan, does a sequential scan. What is a sequential scan? It's exactly what it sounds, sequentially scan the table. Okay? If I do a D, which is in the middle of sort of the values, I get a bitmap index scan, kind of nice. And if I do a K, I get an index scan. So this is what I expected. An index scan is going to kind of go through. Bitmap index scan is going to basically create a bitmap of all the matches and then go to the heap table to get the results. So sequential scan is straight across. Bitmap index scan is in the middle. It makes a bitmap and then goes to the heap. And the index scan just goes directly from the index to the heap. Okay? That's what we would expect to see. In fact, I can write this query and I can see that depending on the value, I get different outputs. So if I run this query, I get this slide. And what this slide is showing me is that the common values, the P, the S, the C, and the R, generate sequential scans. T all the way to U are bitmap heap scans, and E to K are index scans. Okay? It's kind of easy to see. As the value gets less frequent, you get different outputs. Now, you could actually force an index scan on every entry. If I issue these commands here up at the top, then you'll notice that the P actually now has a cost of 39. It used to have a cost of 13. So by forcing an index scan, I've gone from 13 to 39. And that query is going to be slower. Okay? Now, you can test that. You can run explain analyze or timing. It'll actually time the query. So you can play with this. You can try turning off access values to see if it's faster or not. Typically, the system's pretty accurate in determining which one is going to be fast enough. Okay? So, but that's a good example. The 39 to the 13, you can kind of see it's a different thing. In fact, you would think that, for example, index scan is only used when you have like 3 or 5% in the index. The sequential scan is very fast because it can sequentially read through the table real quickly. Index scan, it's got to read this block and then this page and then this page. There's a whole bunch of reading to go on just to get to the row. So again, if you're looking at a constant that's 10, 15% of the table, it's going to be faster to do a sequential scan, even if an index exists. And that's often a surprise to people. But if you actually run the timing and you force an index scan, you'll see it does indeed get slower in this case. It's often a surprise to people. Okay? What about join methods? So that was the second thing I said was important. There are actually 4 different join methods. There's a nested loop, which has 2 types. There's a hash join and a merge join, and I'm going to show those to you. First, let's create a table, 2 tables. One is made from the proc array. and it basically loads up. And this one is from sample 2 from PG class. So I've created 2 indexes, no statistics. And if I run this query, it does what's called a nested loop. What is a nested loop? It basically says compare every row to every other row. Now this is fine if the tables are small, but as you imagine, if there's 1 million rows here and 1 million rows there, that's 1 trillion comparisons. Not going to finish very quickly, is it? So again, this is fine for very small tables. That's what the pseudocode looks like. What about this query? This one is saying greater than 33. Okay? And that one is generating a hash join. What is a hash join? A hash join is where you hash one side and then you look up matches from the outer side. You basically hash the value and you look for matches within the bucket that you hit. Databases love hash joins. You see them all, not just Postgres, all the databases love hash joins because they're faster typically than nested loop, which can be very slow for large tables, but they're not as expensive as merge join, which I'll talk about in a minute. So it's kind of in the middle, kind of an option. So you see these a lot. That's what the pseudocode looks like for it. And finally, this query, which doesn't have a where clause at all, does what's called a merge join. In a merge join, you sort both sides, and then you walk through the comparison. So I say, does this match the first row? Yes. Does this match the second row? No. Okay, I can move down. Now, because they're sorted, I don't need to go back to the beginning. I know there are no matches before where I stopped. So I can just look, do I have a match there? Yes. Do I have a match there? Yes. Do I have a match there? No. Okay, I can go down here. I don't need to start at the beginning. I can start where I left off. And I walk basically synchronized through the 2 tables. Very good for large tables. Although the sorting can be expensive, it's probably the most efficient way for a lot of cases. Any questions? I guess this is more simple after the after the other one. Like, oh, this is not bad at all. This is what the pseudocode looks like for a merge join. Again, you have to do the sorting at the beginning. What if I say sample 2 first and then sample 1? Well, actually, that makes no difference. Postgres is a cost-based optimizer. It doesn't care what order you specify the tables in. It'll automatically do that for you. Okay. Now we're going to add some statistics. As I said before, we didn't have statistics before, but now we do. So this query, which used to be a merge join, is now hash join. That's because the system has statistics to know exactly how big the tables are, and it knows it doesn't need to do a merge join anymore. You can even do a hash join with a right outer join. You might think of outer joins don't work, but depending on how you do the outer join, you can still do a hash join with it. The hash join has to have the hash on the inner side because of the way the outer has to work. Okay. Cross join. Has anyone ever used a cross join here? Yeah, very rarely used. Cross join is an SQL standard term which says join every row to every other row. Okay? And as you can imagine, it uses a nested loop because that's what we're doing. We're asking for a join of everything to everything else. Kind of interesting. Now let's add some indexes because we didn't have those before. Now if I do this query, which used to be a nested loop with an index scan, now I'm doing, nested loop with inner index scan now possible. Now I can do an index scan here. Okay, before these were sequential scans, all of a sudden it's become much faster because I'm not comparing every row to every other row anymore. I can use the index on the outer side, and then I can use the index on the outer side to find the row, and then I can use the index on the inner side to find the matches. You can see it's completely different performance characteristics than doing sequential scans with this. Okay? And this is the pseudocode for that. Another case. you might remember that when I created this table, I used an integer, and then I used 250 x's. Do you remember that? I said repeat x. So it's an integer and then 250 x's. So the row has a length to it, width to it. Okay. Now, if I ask for a's, which are not x's, okay, I say give me a's that are in this field. The system these statistics know that there are no a's, but it's gonna give me the benefit of the doubt, and it's gonna say, I'm gonna assume there's one A, okay, and I'm gonna do a nested loop and an index scan to find any matches for an A, but there are no A's, but it knows it probably is gonna make pretty fast because there's very few A's. If I do this with X's, however, I get a hash join because it knows there are 260 X's there, and it knows there are, where is it, 2200 in the other table. Okay, so kind of interesting. Even though this is not what we're joining on, it affects the type of join that is used because it affects how many rows it thinks it needs to process. Okay. The final thing I want to talk about is limit. There's a limit clause in Postgres, came from MySQL. Normally when you run a query like this, you're going to get a hash join. But if you add limit 1, you're saying I only want one row of the join. Now, it'd be pretty expensive to do a hash just to get one row out. So we're like, oh, let's just do nested loop and use the index and just pull a row and we're done, right? You might not have thought that limit actually gave you optimizer value. It does. So some people typically, without limit, they would open a cursor and they would fetch 1 and they close the cursor. But when you open the cursor and fetch 1 and close, we don't know how many rows you're going to fetch. You might do another fetch after that, right? But when you specify the limit, you're telling the optimizer, I really only want one row, and the optimizer can use that to its advantage. That's a great example. So limit 1 uses a nested loop. Limit 10 uses a nested loop. When I get to limit 100, it's like, okay, I got to use a hash. So there's a point at which it kind of stops. So I know that was kind of fast, but what I wanted to kind of talk to you about is that flow of data. Like the way I think of it in this slide is the optimizer is trying to find the fastest way down the river. And it's going to basically go, okay, I want to do an index scan, I'm going to do a hash join, and I want, how can I get to that bottom as quick as possible? That's the way water flows. It finds the quickest way down, down the thing. What questions do we have? I know we didn't get many questions on that one. Is that was all clear to everybody, I guess? Or?
Does it depend on the size of shared buffers or maybe some other caches?
So does it depend on the size of shared buffers? Yes, it does. The optimizer knows how big shared buffers are because it's defined in the server. It doesn't change. It also is influenced by effective cache size. Remember I talked about effective cache size in the previous presentation because it tells me how much, not only how big my shared buffers are, which I know, but it tells me how big my kernel cache probably is. And that influences how expensive I/O is. And that influences whether I might use an index or not. Because if I'm going to use a lot of indexes, I want that index to mostly be in memory. I know how big shared buffers are, but if you define effective cache size right, I also know how big average, it's going to change, but on average, how big my kernel cache is. And I can then favor index scans because of that. There's just a lot of science behind this. There's a lot of sort of numbers that you have to calculate. When you look at a slow query, sometimes it's not clear why it's slow. Like maybe the statistics are bad. Maybe there's a correlation between two columns that Postgres doesn't know about. Maybe effective cache size is too small. Maybe random page cost is too high or too low. Maybe there's no missing index. So there's all these criteria that you have to kind of go at. And if you run explain, you can see the plan and you can kind of guess, well, why is this slow? So what I normally tell people to do if they're analyzing their queries is to take, there's a tool called PG Badger, which is like a command line tool for Postgres. And what you can do is you can turn on logging of all your queries for a couple days. And then you can take those logs and you can load them into PG Badger. PG Badger will tell you which queries are taking longest, which queries are called the most often, and which queries, if you multiply the time of execution by the number of times it's called, are taking the most resources. And what I normally tell people to do is to take a look at the top queries in that last section. Sometimes the long query that runs 10 minutes, if it runs once a day, not typically a problem. But if you've got a query that takes 500 milliseconds and it's run 20,000 times a day, that's a query I want to optimize. And then you're going to want to run explain. You want to run explain analyze, which will show you the difference between the estimate rows and the actual rows. And you can kind of compare. There's actually a website, Depez, which is the guy's name, just a depez.org website. And it allows you to upload a query plan and it'll color it. And it'll show you where your estimates are wrong and where in the explain plan you might need to look. Because again, it could be a whole bunch of problems in there. It could be the way the query is written. It could be missing indexes. It could be a correlation problem. Frankly, 90% of the problems that we see as a community are cases where the statistics are fine, all the settings are fine, but the query is restricting 2 columns in a table. And the columns are somehow correlated. For example, if I ask for Philadelphia, Pennsylvania, which is where I'm from, there may be a lot of customers who match a city of Philadelphia and a state of Pennsylvania. But if I ask for Philadelphia, Arizona, there's nobody. There is no Philadelphia, Arizona. So sometimes when the system looks at how many Philadelphia, Pennsylvanias there are, when you do Philadelphia, Arizona, it's just looking at how common is Philadelphia and how common is Arizona. It doesn't understand that the 2 combinations are very rare. So in Postgres 12, we implemented something called extended statistics, which allows you to create an index on multiple columns in the same table. So that you could create a city-state index on both of them. And when you say Philadelphia, Pennsylvania, it knows that's common. It knows Philadelphia, Arizona is not. So that's a good example, I think, of a common optimizer problem, a case where the column statistics individually are fine, but the combinations are not computed by default. But you can do that with extended statistics. Yes?
Does it help to the problem when we are partitioning our table, large table, by some discriminator and trying to maybe hash join this table with another big table?
So the question is, does this help if you've partitioned your tables and then you're trying to join the key of the partition with another table? So Postgres automatically knows which partitions to join, so it'll throw away all the partitions that don't match the key that you're interested in. So what I'm saying is if you have 100 partitions, Postgres will eliminate 99 of them right away. And it'll only join the partition that potentially could have a match with the other table. So that pruning of partitions is already done by Postgres. It's gotten better and better each year. So Postgres 12 is better than 11. 11 is better than 10. But Postgres 12, for example, is very good at pruning thousands of partitions and only going at the one that potentially has the value that you need. Other questions? Oh, yeah, sure.
And what will happen if I define my user type and values of this user type will not be compared in the transitive way. I mean, for example, I define my user type like colors, and I say red greater than yellow, and yellow greater than blue, but blue greater than red. So I have a cyclic graph, and I will try to build the B3 index on these values, and I got some index, and how Postgres will find some values from my user-defined type.
Your index will fail. You can't create an index like that.
But on the conference,
I mean, you can. You can, but
Postgres will build the index and will use it in some way, but
yeah, but so I see what you're saying. He's talking about the transitive property. It doesn't an index that doesn't have transitive property. None of the Postgres data types will do that, but you're right. You could potentially create an index like that, but the results you get back would probably be incorrect. It won't work well. It's kind of a requirement that there be a transitive. It would break badly, I'm afraid. Yeah. And you might think that's a funny question, but with UTF-8, we've had some challenges where some operating systems weren't transitive for certain characters, and that was like a huge problem. And they fixed it, but we had to clean up the indexes like it was a mess. So there was one operating system, I can't remember what the language was, but they had some characters that weren't transitive in the UTF-8, and we're like, okay, that's just broken. Like we can't, and fortunately it was fixed in the operating system, but they had to re-index all their indexes because there was this weird behavior. I think there was a minor release that did talk about that. And in fact, there is a tool that will detect a non-transitive index. So there's a catalog checker, AM check, called AM check. It's part of Postgres, can contrib. And AM check will walk through your index to make sure they're transitive. And if it finds they're untransitive, it'll warn you. So it's not a completely crazy. Sounds crazy, but there are real-world mistakes that people make that actually cause that, and we do have a tool to detect it. Good question. Other questions? Yes, sir.
Can you say how Postgres database works, like a process, if there are a lot of binary large objects stored in the database? Is it affects speed of the other process or other queries?
Sure. So Postgres has two binary objects. It has standard text data type and byte A that are stored in the row itself. Okay. And Postgres has a feature called toast. Unfortunately, I don't have a slide. Do I have a slide? Oh, I don't think I have a slide. Anyway. It has a feature called toast, which means that if you're looking at a row, any field that's over about 500 or 600 bytes potentially can be stored in a backup table called a toast table. So for example, let's suppose you have an employee record and you have a picture of the employee, right? And the picture is going to be big compared to everything else on the table. So what Postgres will do is it'll store the employee name and their ID and all the information about the employee except for the image. And the image will have a pointer, and the pointer will point to a spot in the toast table. So if you do a sequential scan through that table, if you don't ask for the image, we don't even read the data. Okay? This happens automatically. You don't do it. But anytime that row is inserted, it'll take the long values and put them in the toast table. If you ask for the image, it will, from that pointer, go get the image and bring it back. Okay, so that happens automatically. There's a second capability of Postgres that it's basically called PG large object, and it's a separate table that can store large objects. So in Postgres, the largest field is 1 gigabyte. But if you want to store something bigger than 1 gigabyte in a field, then you have to use the large object system, and that's a separate table. So the good news is that Postgres by default really kind of takes care of moving the big values out of the row, because normally you're not going to look for them. You don't want to see the image all the time. And it allows sequential scans, and even the shared buffer cache is not carrying around these big images unless you ask for them, and then they come out. So, the example I have in my blog entry is if you just do select star all the time, right? We're going to give you that image all the time, even if you don't want it. So that would be a good reason maybe not to do select star if you have large fields. Just ask for the fields you want, and we won't regenerate the image for you to just throw it away. So I think it's a very good system. We've had it for 20 years, 19 years. People like it. They don't even know it exists. But it solves a lot of problems. Yeah. Other questions? That's a good performance question. I should have mentioned that. I think I do on a later slide.
I have heard that fill factor can decrease the speed of the clustering, but how much? Does it really help?
So you've heard that what will decrease the clustering? Fill factor. So yes, okay. So the question is, does fill factor affect the speed of clustering? So you can set a fill factor on an index, and you can set a fill factor on the heap as well. If you set a fill factor on an index, typically it'll prevent splits from happening as much. Although normally the fill factor for an index is probably fine. You don't need to touch it. You are absolutely right that if you're doing a lot of updates, you are better off using a lower fill factor, because if you're doing updates and you have a low fill factor, it will allow you to update the row in place more often, and that will keep the clustering more current. That's a great point. Yeah, thank you.
Like which value?
Yeah, I would say 80% or something. Nothing huge. Don't do like 20% or 50%. I mean, those are just ridiculous. But just 20% free space would probably be enough. So I'm saying like 80% fill would probably be just fine. Yeah.
Thank you.
So my question is related to the previous one. So if I build the cluster over some index, how often should I use, maybe after vacuum, or maybe analyze over my tables and my database?
So the system auto vacuum will automatically run to update statistics and vacuum for you, so you don't have to typically worry about that. There is a field that it's called dispersion, and it indicates how clustered the index still is. So if you take a look at the dispersion field in the system tables, it tells you exactly how much you've lost clustering. Because if you run cluster and you look at the value right away, it'll be 1.0, fully clustered. But then as time goes on, it'll start to get less and less and less. So you can set up a little cron job to say when that table's clustering gets below 80% or 60%, then you get a notification, I need to run cluster. Run cluster, yeah. You can just run a query that pulling off all the tables that have a cluster value that's lower than a certain field.
And is it accessible from maybe some standard statistics?
Yes, it's in PG class. It's in the system table. Yeah. It's called dispersion. It's called dispersion because it's trying to say how dispersed the thing is. But if you look at, if you look at the cluster manual page, I think it mentions it. But I know we record in the system tables exactly how much clustering is still left in the table.
Okay. So if I have a large table and I build some cluster over the index,
Right.
and I have a lot of modifications, I should reduce fill factor, yeah, for index.
I would, fill factor for the heap, yeah. If you're doing updates, yeah.
Complex index that help me to restrict my select from clauses with and maybe, I mean, union or disjunction.
I'm sorry, can you ask the question?
For example, I try to filter my values on one attribute and by another attribute, and these values from these attributes should be between some values. What kind of index should I build?
So the question is, you're running a query that you're doing like a range of values, and should I use a union for that, or an or clause, or a between clause, right? And the answer is we don't know. The bottom line is when you're running a union or an intersect, you're literally telling the system, I want to run this query, I want to run this query separately, right? When you use an and or an or, you're kind of expecting the system to figure out. And sometimes it figures out fine, and sometimes it doesn't. It maybe doesn't use an index because it doesn't think it's restrictive enough or something. And sometimes you know better, and using a union is faster. But there's...
It's very similar to our index, because I try to cover these values
With an R tree, yeah, R tree.
Yeah. And maybe I could build some complex index on these attributes and...
I see what you're saying. Well, not only do you have to... So the question is, he's thinking, should he create an R tree that has like a bounding box for these range of values? You can do that, but you also have to teach the optimizer to use it. That's part of the problem. You can build the index, but then you have to make sure the optimizer understands how to optimize a query. And I've seen cases, for example, where you're doing a query and you do A or B or C. The system runs great. And then you say A or B or C or D, and all of a sudden it's like, what happened, right? It's not using the index anymore, and because the statistics are only so precise. And sometimes you get that case where you add the extra thing. It's like, and then all of a sudden, so I'd love to say that the optimizer always does the right thing, but I've found that the ORs particularly, and that's why I mentioned OR like right here. The ORs particularly, or an AND with a self join, I find is like really slow because it's like, it doesn't really know. It has to go back to itself and stuff. So that's why a lot of times the intersect is a cleaner way of going at that than a self join. But I don't have any rules for that. I just know that I think it helps, but you have to test both of them. No, it doesn't depend on the order, but I'm saying sometimes when I do ABC, the costs from the optimizer says index or hash join. But when I say ABCD, when I add another OR clause, then the optimizer is like, oh, I want to do a merge join. I'm like, whoa, no, don't do that, right? So the ANDs and the system does really well with most queries, but the problem it has is when you're using a lot of ORs, it doesn't really know how related those values are, and it's trying to kind of add them together. Because if you say A or B or C, then you have to take the probability of A, add it to the probability of B, and add to the probability of C. But if you do A, B, C, D, E, F, then it's like, okay, now I've added a whole bunch of probabilities, and it's like, well, and also if the probabilities are different columns, like, okay, if column 1 is A, or column 2 is B, or column C is 3, like, well, maybe column 1 is also A when column 1 is C. Maybe when column 1 is A, column 3 is also 3, right? So it gets into the Pennsylvania, Arizona problem where you've got a correlated thing. And typically in those cases, I'm going to recommend a multi-column index, because then I have statistics for A, B, C, and D, and then the optimizer is going to make the right decision. Does this make sense? So normally if it's the same column with a bunch of constants and ORs, we're good. But when it's one column and a constant and then an OR and then another column and another constant and then an OR and another column and another column, the system doesn't know how often the first match also for the same row is the third match or the second match. and it's going to guess, but sometimes it guesses wrong, like Pennsylvania, Arizona, right? So if I say equals Pennsylvania or equals Arizona, it's like, how many? That's where the optimizer, that's where you need multi-column statistics, I would say. Now you can get around it with a union, but you're probably better off in that particular case using the multi-column statistics so that we have absolute numbers and the optimizer knows how common that OR is. If that makes sense. Actually, I take that back. That wouldn't help because the OR, the AND would help with the multi-column, but the OR, no, the multi-column won't even help there. And this is this is not just Postgres. Every database is going to have this problem because there's no way to compute A is 1 or B is 2 and C is 3. Like, how do you create statistics for that? You have to create a whole three-dimensional like array of it's way too complicated. And that's why sometimes I'm saying you actually do have to kind of roll up your sleeves and try something else. Yeah. Other questions?
So you gave us a lot of knowledge, but in order for the project that we work on front, we need to not only have this knowledge but apply it. And what changes in habits you would advise for the developers to take in order to have a project that optimized and have good performance?
So what changes would I recommend for developers to make sure that they kind of are able to follow these and they're able to stay? That is an incredibly hard question. What I normally tell people is that the creation of the data model is probably the most important part of the application. Okay? I was talking to Yvonne about this earlier. A lot of times what happens is you create a data model assuming a certain workflow. And that data model works perfect for that workflow. The indexes are in the right place, the columns look good, everything's normalized, right? But as the application adds features, you start to drift away from the data model and you start to have missing indexes, you start to have to do awkward joins to enable features. So what I normally tell application developers is spend your time up front creating the data model, but also be willing to change the data model as your application needs change. Because if you don't do that, and I've seen this many times, it'll be year 5, and you will be writing horrendously, terribly long queries to do what should be simple. But because the data model hasn't evolved, people don't want to change the data model once the application's deployed usually. But if they don't change the data model, then the queries become more complicated and more complicated. And then the application programmers are asked to do this kind of weird, all these weird things, right? And I think the other important thing is that not every application developer needs to understand this. You just need one person to keep an eye on it, right? I don't think most people are going to be able to keep this in their head. I don't think it's necessary. But as I said before about dysfunctional families and dysfunctional databases, it only takes one person to realize that that query is really ugly and it's not working well. You don't need everybody to realize it, just one person to tell them. And then we need to have the strength to correct it, because over time, I know it's hard to change data model. Just add columns and add indexes. It's sometimes difficult, but it makes your job easier in the future going forward. Sometimes you even have to take downtime because you're going to have to restructure a table into 2 parts maybe, or bring 2 tables together. And it's going to be downtime. But ideally, every 6 months, a year, you would look at your data model, you'd look at your queries, and you'd say, we really need to take some maintenance here, and make our data, if the data model is clear, the hardware's in the right place, the database settings are in the right place, the queries kind of write themselves if the data model matches. If the data model doesn't match, then you're doing a lot of gymnastics. And usually the solution is to update the data model. That was, in general, that's what I think. I don't think everyone needs to do this, but they need to be willing to update the data model so that application queries are simple for people. And if you look at most applications, when they start, the queries look really good. By year 5, oh boy, a lot of people don't even know what the query does anymore. There's just so much in there, and there's so much conditional logic, and it just, you know, and people people slow down. They don't want to touch the query because it's like scary, because I don't know what it does. So I think that's really the key. It's a great question. Nobody's asked me before, but Yvonne and I were just talking about it. Great. Yes, sir. I think probably the fill factor is the one I think the most, because the fill factor will allow for updates in place. That's probably the only thing I can think for an update workload. The only other thing I can say is that with updates in place can only happen if you're not updating indexed columns. So the other point is that if you have an index on a column that you don't need, and you're updating it a lot, you might want to drop the index so that you can do what we call heap-only updates, called hot updates. And you can see those. If you look at the statistics, there's a field called hot updates, and you can see how frequently the updates were able to be done in place. And if you have too many indexes or a high fill factor, maybe that was not possible. Okay, great. Thank you.